So you can see everything looking at the full view.
It looks perfect. Go ahead.
Beautiful, thank you. Yeah, well, so it's a pleasure to be here and to be here at least virtually, I guess. We're still in that time of life now. But nonetheless, I'm excited to tell you a little bit about this project that we worked on. Started about 2 years ago and sort of ended just as I was graduating. And it's about how weak measurements can be used as a tool for reconciling what we might otherwise think of as incompatible observables. So the outline of my talk is basically just going to break down this title. I'm going to start off with weak measurements, describing what we mean by quantum measurements, how those work in practice, and how they work in reality, I guess. And then I'll talk about the incompatible nature of some observables, especially quantified by uncertainty relations, Heisenberg uncertainty, other kinds of uncertainty. Then finally, I'll get to the good stuff, describing how we've been able to reconcile two otherwise incompatible observables, and that'll be the experiment that I detail. So I want to start off with a quick description of the interesting parts of quantum measurements. And by quantum measurements, maybe we mean just anything that measures a quantum particle, a quantum system. And to keep things simple, and because I'm a simple experimentalist, I'm going to talk about sort of the simplest quantum system, a spin 1/2 particle, where there are only two possible outcomes, spin up or spin down. And the measurement process, you might follow something like this, this classic Stern-Gerlach apparatus, where we send the two spins down a trench in a inhomogeneous magnetic field, and those two spins get projected onto the back end of a screen. This, of course, corresponds to measuring the sigma z component of that spin. And if we look at the screen results, we see that we get two distinct blobs, one blob corresponding to, say, spin down, and the other blob corresponding to spin up. Nothing too surprising here. Maybe a little bit surprising that we get two blobs, but we sort of put two inputs, get two outputs. It's, I think, fairly straightforward. The strange part happens, and so, sorry, each of these blobs has different expectation levels. The strange thing is when we then put in different states. In this sort of semi-classical picture, this might be a left-pointing state, or in a more fully quantum view, we might think of it as a +X superposition state. But the surprising thing is that these measurements distribute, again, according to these two different blobs. Of course, this is classic quantum mechanics, a bit of an oxymoron statement there, but we nonetheless understand this. We've prepared a sigma x eigenstate, and so the sigma z measurement of that is incompatible. And so the two outcomes are sort of, let me back up. When we put in this left spin, the outcomes of whether that particular spin would land up or would land down was a totally random process. There's no way to predict whether that sigma x eigenstate will measure z +1 or z -1. And that total randomness comes from the fact that sigma z and sigma x are, in a sense, maximally incompatible. And so the question that I'd like to answer in this talk is how we might be able to mitigate that kind of measurement incompatibility. And the answer will be that if we add measurements, specifically if we add a weak measurement, that we can do a little bit better than what the sort of traditional view of these two incompatible observables would say. And so to do that, I need to tell you a little bit about how we do measurements in practice. And this is a pretty interesting question because we live in a fairly classical world. And so it's difficult to lay our grubby classical hands on delicate quantum states. And so it's obviously not enough to just to wear gloves. We put it in a dilution refrigerator to really isolate it from any fluctuations, thermal or any other kind. But the real way that we perform these measurements is by using a pointer. And so we, in any kind of realistic picture of a measurement, there's always some physical interaction between the system that we're interested in and some measurement apparatus, some pointer. And so the delicate superpositions or quantum system, all the properties there, are conveyed through a pointer into this sort of classical meter that will return the 0 or the 1. So we can be as delicate as we like in the interaction between the system and the pointer, and then as destructive as we like in between the pointer and the meter. And that gives us a wide range of control about how this measurement unfolds, what kind of measurements we do, and I'll describe that in just a moment. And so in this Stern-Gerlach example, the really, I'd say, ingenious part of this experiment is that it couples this spin degree of freedom, this quantum mechanical thing, with the position of the spin at the back of the device. And so this spin up or spin down state is in some sense measured continuously over the long distance of this trench. And so the ingenious part of this is that it's figured out a way to take this quantum mechanical thing, this very delicate spin system, and in some sense magnify that or pull that out into a different degree of freedom that can then be measured more easily, more destructively, and ultimately more informatively. And so this gives us a sense of the kind of tool that I want to introduce, which is a partial or sometimes a weak measurement. And this partial measurement is something would be relatively straightforward, I think, to do in this kind of Stern-Gerlach example. And that would be just chop the machine in half. So with a shorter trench, the two particles will not be distinguished as much, won't deflect as much. And so the two blobs corresponding to the different expectation values will be closer together. And the signal here about which state the particle is in is not so clear. In the case that we send in this sigma x state, we again get a distribution that's centered on, that has two centers corresponding to each of the two sigma z eigenstates. And again, that outcome is totally random. However, the fact that we put in a left pointing spin or a sigma x state, and we ended in a sigma z state, tells us that during this measurement process, there was actually some change to what the state physically was. It went from being plus x to, say, being plus z. And so in this partial measurement, or if sort of the trench is short enough, we might call it a weak measurement. In this weak measurement case, the x pointing spin is not as disturbed as it would have been in the case of a stronger measurement. So this highlights another component of quantum measurement, namely that there's not only measurement incompatibility in that the outcomes of measurements of the z measurements of the x state, not only are those measurements random, but they actually change the state. This is well-known back action that we may be familiar with. And so this is, but I want to highlight that this is sort of a separate issue, that the disturbance to the wave function is separate from the randomness of the outcome. And so there's another feature here, disturbance uncertainty, that these weak measurements help us address. Okay, so that's sort of a very quick version of quantum measurements. Let me tell you a little bit about how those measurements work in practice. So this is a superconducting qubit experiment. And so we have a transmon circuit printed here on a silicon substrate. That's this dark gray chip in the middle of the frame. And that is coupled to a microwave cavity that we machine in-house. And so the quantum system, or the spin, is realized by this transmon qubit. And the pointer is realized by the intercavity photons that will pass through this cavity. And so the way that we perform this measurement to figure out what the state of the qubit is by sending in a coherent state of light into the cavity, allowing that state to interact with the qubit for some amount of time, and then bring it out the other end. When it comes out, the interaction between the qubit and the cavity, or the cavity photons, causes a qubit-dependent phase shift on the state of the cavity. So this coherent state that was aligned at 90 degrees now gets shifted forward in phase or backwards in phase, depending on whether the qubit is in the excited state or in the ground state. And when these two blobs are well separated, we say that we've projectively measured the qubit because we know exactly what the state of the qubit is after the measurement. Now, in this same platform, same experiment, we can simply turn down the number of photons, effectively weakening the interaction. And in this case, our two ground and excited state distributions now overlap fairly significantly. And so in this case, because we don't get full state information, we only have a partial measurement in that we can't say certainly whether the ground is in, whether the qubit's in the ground state or the excited state. So that could be seen as a problem, but in our case, we're happy that we don't disturb the qubit very much. So with this partial measurement, we have a way to sort of update, update our state of knowledge about the qubit, but we haven't destroyed the state that the system was in. Let me describe that in a little bit more detail. So here again, we're putting in this weak measurement, this low amplitude coherent state, and we have the state dependent output from the state. If we histogram just one of these components of the field, say the in phase component, that's I, we get a Gaussian histogram for each measurement we'll call little j, and that distribution is sort of really the sum of two Gaussians centered at +1 and -1, but the variant, we tune the variance experimentally so that it looks more like a single Gaussian. Now, if we put in a superposition state, so that's this sigma x pointing state on the block sphere, so we start off with a state and we update our state after every small measurement outcome j. So we have a formalism that we use to update our state of knowledge about the qubit. And that's sort of with this standard density matrix evolution with measurement cross operators m sub j corresponding to the whichever measurement outcome obtained. And the important part here is that the measurement operator is a Gaussian weighted sum. So this Gaussian weight applies to a variety of projectors of the qubit state. And so the way this weak measurement works, mathematically at least, is that we're projecting onto a wider basis that the photon state provided us. So we have lots of different options for what the qubit measurement outcome will be. And because those many measurements, many possibilities don't correspond to fully collapsed qubit states, we get just a partial, partial update of our state. Let me explain what that looks like in a more kind of graphical form. So imagine that we're looking at this measurement outcome, and the first sort of small chunk of the measurement has a slightly negative value. From that negative value, we know that the qubit is more likely to be in the excited state than the ground state. So we take our state of knowledge and we update it slightly to be closer to the bottom of the box here that is the excited state. In the next sort of instance of time, next dt step, we can get a much larger outcome. Now, this is a random variable and it fluctuates around, so we can get these positive values. That brings us to some position much closer to the ground state of this empty box. And then we can continue getting negative values and continuously updating the state. Excuse me. Now, this measurement update process is, I hope from my little graphical description, is a continuous process. The state evolves continuously. And it's also deterministic. That is, for any particular value of j that obtains, we know exactly how to update the state of the qubit according to that measurement. Now, that outcome is random, and so it's sort of random input, well-characterized process to update leads to a well-known outcome. So if we could somehow control those incomes, then we could control the outcome. Okay, and so that's kind of the basic process of using these weak measurements for feedback, and conveys how this partial information is supposed to give us partial back action.
Can I interrupt? Can I interrupt the question, please?
Yes, go ahead.
You do sequential measurements, but you reset the system to sigma x between each measurement, or you measure and then you do not reset the system?
Yeah, good question. So there are two options. We can do both. This process that I'm just describing is taking a long measurement and chopping it up into multiple measurements. So we would take, say, a microseconds worth of these signals, and we would update every, say, 10 nanoseconds or something. So it's a continuous process of measurement. Did that not answer your question?
No, I'm still confused.
Sure.
The question, the thing I'm trying to understand is whether the state that you measure at a little bit later time, which is what your delta t is, if I understand correctly,
Right.
is the same state you started out with, or it's the state that you already influenced by your former measurements?
It's the latter case.
Okay.
Whatever measurement at 2 dt depends on 1 dt.
Okay, thank you. Thank you.
Okay, so this weak measurement offers a strategy for doing you're getting partial information and imparting partial back action on the state. Oops. Okay, so now let me tell you about how these weak measurements enter into uncertainty relations.
Do you mind if I, sorry, jump in just to voice a question that was typed into the chat, but I think other people probably have the same question. You said we know how to update the state. And the question from Noah is, do you mean that you're updating your classical prior, your information about the state, or do you mean that the actual, reality, the quantum mechanical description of what's out there is changing?
Yeah, it's a great question. I think it's one that's very hard to answer because all we have really is our classical information about the state. And so I would take the kind of philosophical position that those are equivalent, that the state really does change according to our measurement. But that's, I guess, more of an opinion than a technical point. And
Wait,
I don't.
If I can, just jump in and clarify a little bit. I'm kind of echoing Paul Brummer's question to some sense, but there is a philosophical question, but that's not what I'm trying to ask. I'm asking, like, when you do the experiment and you're saying we update the state and you have this drawing of the sigma z, sigma x flipping around, is that you just have a computer memory somewhere which is keeping track of these flips, or that like the mode in the cavity is changing in these jumps? Is that, I don't know if I asked that correctly, but
yeah, I think I'm getting your point. Maybe, yeah, I'll answer it by saying that all of this is done sort of in post-analysis. That we take a noisy trace of j versus time, and then we sort of ask afterwards, what happened while we were measuring it.
got it. Okay. Okay, thank you.
Yeah, there are interesting cases where you use like an FPGA located at the bottom of the fridge to say, take this input, take this voltage, process that, and send a feedback signal. And so that gets a little bit closer to sort of the spirit of your question of how, whether the state really is changing. And so I think some experiments that are sort of coming online now where this low latency feedback is being realized, I think may answer your question a little bit better.
Okay,
That's
that
really
helps.
interesting.
Sorry, now I feel obliged to jump back in. And sorry if I made it sound more philosophical than was intended. But if I understood your answer there, aside from the philosophical question and the fact that right now you do it in post-processing, which is just a question of speed, if you were just tracking this continuously, not doing feedback, but just tracking it, then at every instant, you would revise your best estimate of the density matrix and say, right now, that's my best description of what the state is probably doing. And maybe philosophically, you even think that's the correct state. But regardless, what you're doing is at each instant in time, making your best estimate of what the state must be given the measurement trace you have so far. Is that accurate?
Yeah, that's right.
So now I'm confused. If you're not measuring the state that if you're doing what I understand you're doing, which is not resetting the state after each measurement, then you're not measuring the state that you originally had, right? You're measuring how the state has responded to previous measurements, as opposed to what the state is, right? So now I'm confused as to what you're actually measuring. Maybe I should rephrase that. If I reset the state every time, I know that I'm making a measurement on the state that I'm interested in. If I don't reset the state after each measurement, then I'm not measuring the state that I was interested in.
Right. So maybe another important piece of information is that we start off in a known state. We definitely start off in the +X superposition state. And as this measurement unfolds, we're gaining, so I'll say that we start off excuse me, with perfect information because we prepared the state well. And as the state evolves, I'm saying that we know exactly how, given a measurement, an interval dt, how do we update, I guess, our state of knowledge about the state from that measurement.
Can I try something? Since I've been arguing with Paul for 20 years anyway, I have some insight into this.
Discussing, we've been discussing, not arguing, discussing, yeah.
Well, we can argue about the semantics later. What if we began in the +X state, as Jonathan said, and we did a traditional measurement. I just measured S sub Z. Well, then I would find either up or down, right, which wasn't the initial state. Would you have said, oh, well, then I'm not really learning about the initial state. I'm learning about how I disturbed the state with the measurement. If that's the tack you want to take, then that's also true for the weak measurement. But otherwise, you could argue that he's little by little revealing that result that was going to appear anyway. You're learning in some sense that it was Z, even though you prepared it in +X.
I don't want to take up all this time, but let me just say that, if I'm trying to measure your height, right, and I do it by banging you on the head, and then you get shorter as a consequence, and the next time I reset your height and bang you on the head again, and so on, I'm measuring your height. But if I bang you on the head and you get shorter, and then I measure your shortness, and then I bang you on the head again and you get shorter, I'm not measuring the original state. I'm measuring the interaction between the measuring device and the state, which you may be able to disentangle, but that's not what I see is happening. There's no disentangling here of the measurement and the state. Let's put it a different way. If you use a different measuring device and you did the same thing as is being done now, you'll get totally different results. But if you did the old kind of projective measurement, presumably when you keep setting, resetting, you will get directly the same measurement of the same state. I just don't understand what's being measured here. That's all I'm trying to say. And I better shut up because it's not my, sorry.
No, this way we'll get to see whether Jonathan gives the same talk if we keep banging him over the head. But
yeah,
I'll shut up also,
exactly.
and I think it's better this way.
Okay,
and by asking questions, you get different answers.
If I may, just one more very down-to-earth question. In the animation with the red pointer flipping around, is that
Mhm.
red pointer just like the direction? Like, okay, in each J, you apply these cross operators to row. And so is the red arrow just the block vector of that updated state? By doing
Yeah.
cross? Okay.
Yeah.
And so should it, I mean, obviously this is just an animation for, and not, you don't need to put all the details on there, but if you were to put an extra detail, would the block vector be like mixed? Would it be shorter than all the way onto the circle?
Yeah, that's a great point. And yeah, will turn out to be a key part of the physics here.
Okay.
And so yes, that's shorter.
Got it. Thank
And
you.
I think, yeah, you're welcome. I think that also will come to answer Paul's question about what is really being measured and what the de-entanglement process will look like. So maybe we'll take this conversation up again in a few slides. Okay, but let me go to the next section. Okay, so we've described a little bit, talked a little bit about what the measurements, how the measurements work, maybe what we're actually measuring. Now let me describe the uncertainty relations that govern these measurements. And so we're all familiar with these kinds of Heisenberg uncertainty relations that relate to the product of variances between two observables A and B. And we know that that relates to the expectation value of the commutator of those two operators. In the spin 1/2 systems that we're talking about, this corresponds to the variance between sigma z and sigma x, and the commutator of those is, of course, sigma y. Now, this uncertainty relation is, of course, true and valid, but it's kind of useless for this sigma z, sigma x case. Because since we've sort of restricted ourselves to just work in the xz plane of the box here, this expectation, this uncertainty relation says that the bound is 0. This 0 bound is the trivial bound because we already know that variances are positive quantities. And so the kind of physics contained in this uncertainty relation don't tell us anything else about how much uncertainty we're required to observe in these two observables. But the problems with this uncertainty relation actually go a little bit further. And that is the fact that it uses the standard deviation to describe uncertainty. Let me illustrate that with a quick example. Here, moving to a spin 1 particle rather than a spin 1/2 particle. So the spin 1 has 3 outcomes, +1, 0, -1. And let's assume that each of those occurs with equal probability, 1/3 in each. If you go through the math, the standard deviation is the square root of 2/3 or something like 0.8. Okay. Now, imagine that you perform a measurement or perform some measurement that excludes one of the possibilities. So now we know for sure that the state is not in this middle state. The probability then of being +1 or -1 has increased to 1/2. Yet the variant or the standard deviation has actually increased to 1. And so despite the fact that we've learned information about the state, we've excluded one of the possibilities, we're actually less certain, according to the variance, about what the measurement outcomes should be. This story changes if the measurement excludes not the 0 case, but the +1 case. And in this case, the standard deviation does decrease to a quarter, about half of the previous value. And so this variance is not exactly the best quantity to describe the uncertainty that we're trying to deal with for these kind of spin systems. And so instead, we're going to move to a quantity that's that we may be familiar with called entropy. So the entropy is, or this Shannon entropy, is the average value of this quantity called the surprisal, or the log of 1 over the probability. And this entropy is beneficial because if events have higher probability, then those are supposed to convey less information about what the state of the system is. in the spin 1 example that I showed you on the previous slide, the more probable the states, the less surprised I am that they occur, and also the less information that I get excuse me, in distinguishing what the state what the sort of the message would be overall. This is coming from a kind of either cryptography perspective or a information encoding perspective, where you think about the probability of a series of bits or series of outcomes. Entropy is also beneficial in that independent probabilities add together, and so you can easily calculate the information content of multiple measurements. And that's not so easily done with variances. Then entropy also has all of these applications in thermodynamics and cryptography and others. And so entropy will be the preferred method that I use to describe excuse me, to describe the uncertainty relations here. And so an entropy-based uncertainty relation might look something like this. This is called the Mason-Ufink uncertainty relation, named after the originators. So it depends on the entropy of observables A and B, and it's bounded by this quantity log whatever. I'll get to that in a moment. So just focus on the left side. Entropy of an observable is the Shannon entropy of the probabilities, excuse me, of each eigenvalue little a. And so so we'll take a state, know what the probabilities of measuring the eigenvalues of that state, of the measurement operator are, and then take the Shannon entropy of that probability distribution. And then the bound here doesn't depend on a commutator, but it depends on this kind of overlap between two eigenstates of the two measurement operators A and B. And we choose A and B tilde so that the overlap here is maximized. You'll notice, excuse me, that this bound does not depend on the state of the system, unlike the original state, which depended on the state based on this expectation value. And so we get state independent bounds for the uncertainty. And so the first issue that I raised about sigma z, sigma x eigenstates having a zero bound doesn't apply here. And then the fact that the entropy is based only on the probabilities rather than on the sort of actual values, the x coordinates, tells us that the problems with the standard deviation that we listed on the previous slide also will not apply, because it's just based on the probabilities, not on the actual values of the spin 0, +1, -1. Okay. And so entropy is this entropic uncertainty relation is what I'll describe now. So in the case of just plain Jane, simple projective measurements, we can derive this uncertainty relation for between sigma z and some sigma theta, which is a linear combination of sigma z and sigma x. And so when I started the talk, I was describing these measurements of a spin up in a spin in a string Gerlach, again pointed up. Oops. And so this excuse me, this measurement configuration has zero entropy. There's no uncertainty about what a spin up particle will result in. On the other side, we sent in a left pointing spin, and this one was maximally uncertain. Okay, so we sent in plus z, that had no uncertainty, sent in plus x, that had maximum uncertainty. Maybe I'll mention this is equivalent to turning the string Gerlach over and sending it straight through. So we have the two extremes, and we also have any sort of position in between. And so this theta measurement, again, will correspond to a combination of z or x, just pointing along some axis defined by this angle theta. In this case, the uncertainty relation is the log of a cosine or a sine, depending on whether theta is less than 90 degrees or more than 90 degrees. Okay, so this is the uncertainty relation that we'll describe. So as a function, so here's what this here's what these entropies look like as a function of this measurement angle theta. Again, at the two extremes, when theta is 0 or pi, the uncertainty is minimal and corresponds to 0 bits of entropy. That again corresponds to the case when we prepared spin plus z, and measured it and got sigma z as +1, unsurprisingly, totally deterministically. Then in the middle, when theta was pi over 2, we were preparing plus z, measuring x, and those outcomes were totally random as a 50-50 distribution, and that probability distribution corresponds to having 1 bit of entropy. Sometimes that's the definition of a bit. And so that's the entropy. Here's what the bound looks like. It's this, again, just this log cosine squared thing. And we see that it's a tight bound in the case of 0, pi over 2 and pi. In the cases that I just described, but there's a bit of a gap in between. And it's kind of an open question in this field of uncertainty relations about how good of a gap, how good of a bound one can derive to make it as tight as possible to match the entropy. Okay, so that's sort of a quick introduction to the entropic uncertainty relation for projective measurements. Now let's get into the real substance of the talk by describing this uncertainty relation for a weak measurement. So in this case, we're not considering, we're comparing, I should say, the entropy between two separate measurements. Again, our original sigma z measurement, and now a kind of composite measurement, where A is a variable that we're going to measure weakly, and then we'll measure another variable strongly at an angle of theta f. So whereas before we just had this single f strong measurement outcome, excuse me, we now have a weak measurement at some different angle theta a. Okay, so let's see what this uncertainty relation looks like. Again, as a function of this strong measurement angle theta f. So the red curve is just the same as the last figure. But now in black, I'm plotting what the entropy is of the strong measurement with the weak measurement coming right before. In this case, the most important point.
Can I jump in one more time? Because that second quantity confuses me, and I might not be alone. So this is after you do the weak measurement, what the entropy is of the results for the strong measurement, is that right?
It's the joint, it's the entropy of the joint probabilities for the two measurement outcomes. Both
yeah,
A
I guess
and,
since I'm thinking of the weak measurement as being a poorly resolved continuous variable, I don't understand what it means to define an entropy for it. So what are the measurement outcomes for the A sigma theta f?
Yes, so we in practice we discretize that signal into like 30 different outcomes or so. And so it's a 30. So before we had a two-dimensional probability, sorry, 2 outcome probability. Now we have a 30 outcome probability.
Okay, but then the entropy in some sense is just dominated by the intrinsic uncertainty of the pointer, or the interaction isn't changing that very much. Is that correct?
That's right. What I didn't mention also is that I've subtracted off the A entropy, just to make a direct comparison to the previous case. So it's entropy of the joint probability minus the entropy of the weak measurement alone.
All right, I'll probably need to think about that more, but I don't want to keep you longer there.
Let me actually explain that a little bit better by going these slides. So the entropy of the operator was the entropy of the underlying probability distribution. And the probability distribution, excuse me, for a single measurement, of course, has single outcomes. But then in the case of a joint measurement, we have two outcomes. For the one is the continuous case for the weak measurement. The other one is the outcome of the strong measurement. So those are sort of two separate outcomes. Those two outcomes define a two-dimensional probability distribution. Then we calculate the entropy over that joint probability distribution. So we're just doubling this index to go both over the weak measurement and the strong measurement.
Okay, but then you're subtracting out the initial entropy of A. So the argument is, even if you begin with a really uncertain pointer, if you measure how much that entropy increases during the measurement interaction, that's really a way of defining what the entropy of the underlying system was. That's your perspective?
Yes, exactly.
Okay, thanks. That's cool.
Okay, so let me draw your attention to this middle point here, where we can compare the entropy of the strong case in the measurement configuration where we've prepared Z and measuring X, and then the case where we prepare Z, weakly measure, and then measure X. In this case, the relative entropy of just the strong measurement, again with this weak measurement entropy subtracted off, has decreased the uncertainty in that sigma X measurement. So this is the core sort of finding of the project, is that by adding this weak measurement before the strong measurement, we can decrease the uncertainty of the strong measurement of the X measurement outcomes of the Z state. Now, this doesn't come for free because the entropy at all the other configurations is significantly higher. And so by measuring the state, by weakly measuring the Z eigenstate before measuring sigma X, we essentially mix other states, but get better information about the sigma X. And so that's sort of the cost of doing this kind of weak measurement. But I want to highlight that question.
Sorry, very quickly. So why doesn't your blue line change with the weak measurement? Like, why are you always allowed to do a strong measurement of sigma Z at the same time? The Z.
Yeah, great. So I should say these quantities are measured separately. The first term of this inequality and the second term.
Okay.
Both measured separately.
And the uncertainty relation holds even if they're done on separate states? Like they're done separately?
Yes, just because in the same way that if you're going to measure, for example, Heisenberg's uncertainty, you would prepare a state, measure a bunch of sigma Z's to estimate the variance. And then you would take that same state, measure sigma X a bunch of times to get that variance. And then you would, in the analysis, compare the product of those variances for that given state, and then see that it's greater than the bound.
Thank you.
Okay, so one element of this uncertainty relation that I want to highlight again is that it is related to this disturbance uncertainty, in addition to the kind of traditional incompatibility that we might think of. So this is the fact that we're sending in this say, kind of upward pointing state. We weakly measure it first, and that changes what the state is, and then we finally projectively measure it at the end. And so the disturbance that the measurement imparts turns out to be an essential feature of how this reconciliation happens between sigma Z and sigma X. Okay, and so we have these two measurement configurations. And so I can measure the entropy at each of these different configurations. And that's what I'm showing here on the right. There's a function of the weak measurement angle along the x-axis and the F measurement, the strong measurement along the y-axis. We get a whole distribution of different entropies. Here I'm no longer subtracting it, and so the entropy has units of values of something like 5 bits or so, corresponding to 2 to the 5 different outcomes. So there's a full distribution here. The entropy is minimum at the places that we might expect when either both measurements are aligned with the initial state, sigma z. When one of them is anti-aligned, measuring minus sigma z has the same entropy as measuring plus sigma z. And then when either of the measurements is pi/2, when we're measuring x in either weakly or strongly, then that corresponds to maxima in the entropy. However, one surprising result is that the maximum of this of the surface doesn't appear just here at pi/2, but it actually has this kind of snaking pattern that the picture doesn't quite show very well. It sort of snakes up here, up to the top here, and then back down and around, sort of like that. And so there's a interesting part of this sort of structure of looking at how this measurement interaction shifts all these entropies. Now, maybe one more surprising fact. So if I offered to if I gave you a sigma z state and asked you to make a sigma x measurement and predict the outcome, in principle, you wouldn't be able to do that because sigma z and sigma x, of course, are incompatible. But if I tell you that you're allowed to weakly measure at whatever angle you'd like before measuring sigma z, what measurement axis would you choose? When I started on the project, I imagined that if I'd like to measure sigma x, I should just measure sigma x, and that will give me the best guess at what the x measurement will be. I'm sort of pre-collapsing the wave function towards one of the eigenstates. But it turns out that the optimal value for theta A is actually pi/4. It's halfway between the two measurements. And to show you how that works, so in the previous slide, I showed you this trace where I chose the optimal value of theta A, and we looked at different strong theta F measurements. And we found that the minimum that the configuration here at pi/2 was lower than it would have been otherwise. Now let me look at just the incompatible case of having this theta F fixed at pi/2, so fixed preparing z and measuring sigma x, but with a weak measurement. Okay, so here again is this entropy with another value subtracted off to make this first point 0. And so as if I prepare z, so this first point corresponds to preparing z, weakly measuring z, providing me no information, and then measuring sigma x, and that entropy is just as high as it was before. There's no change there. However, if then I measure at pi/4, if I pre-measure it at pi/4, that corresponds to my minimum. And then surprisingly, if I measure at pi/2, I've actually done no better than what I would have gotten had I not measured at all, or if I just measured sigma z. To understand this, I'm going to use another cartoonish animation to describe the realistic process of what happens to the measurement. And this goes to your point about decoherence, that as I measure the state not only rotates, but it also shrinks. So the back action, the sort of what I might call a unitary component of back action, rotates the state to be something different. But then there's also processes of decoherence, both unintentional, also just based on the measurement, that shrinks the state and moves it closer to the eigenstate, to the x eigenstate. And so this process turns out to be this process turns out to be optimal when theta A is pi over 4. Like a little bit surprising. Okay, let me skip this in the interest of time. Now let me just jump to the, so this was all discussing the left-hand side. Now let me describe the right-hand side of this inequality. So I put in this innocuous looking F weak. It turns out to be a little bit more hairy than that. There are two terms that I won't get in very much, but I'll just focus on this second term, which is sort of a weak correction to the uncertainty, to the previous value. And the point is that it's proportional to this quantity Wi, which is a weak value. And so in this analysis, a weak value sort of naturally appears as this quantity that bounds this uncertainty relation. So weak values have been a bit of a surprising feature of quantum mechanics, which led to this kind of provocative title about how the result of a spin 1/2 particle can turn out to be 100. Now, I'd say this title is sort of a little bit misleading just because the weak value is not a sort of a traditional measurement as we would think of. It's more of a, it's at least is a pre and post selected, so it's a conditional measurement. And that conditioning, I think, is really what sets this. Anyway, so let me again skip some things. The point I want to make is that this weak value is really just a sort of post-selected and shifted probability distribution, and so it's not as perhaps surprising as maybe it was originally conceived as. Anyway, let me just try to quickly go through this. So here's the details of how we've actually measured this weak value. We start off with some initial state I, weakly measure, and then post-select on measurement outcomes. In this case, where the F outcome, the final outcome, is equal to the initial outcome. In this case, if I look at the weak value, that's the average value of this weak measurement, I get things that are not very surprising. It's somewhere between +1 and -1. And sort of when the angle is 0, measuring Z, the outcomes are +1. If I measure -Z, and the outcomes are -1. Nothing surprising there. But now something more surprising happens when I pre and post select nearly orthogonal states. In this case, if theta F was 150 degrees, so almost fully orthogonal, then in some cases I do measure anomalous weak values, values for this theta for this A measurement that can be greater than the traditional spectrum, greater than 1. Again, it's not very surprising because I have this denominator where I'm dividing by a low probability event, and so the expectation value of this quantity can be greater than 1. Okay, so just again quickly, so we can measure this bound for most of these configurations, and of course, in all cases, the bound, sorry, the entropy is higher than this bound. And you'll notice from the units, from the values here, that entropy tends to be something like 3 bits higher than the bound. And a lot of that is because of decoherence and because of other experimental non-idealities. Now, all of that to say that these weak measurements are, I think, a useful tool for decreasing quantum noise. Some caveats, maybe some interesting philosophical questions. But we've shown how entropy can be decreased according to this use of the weak measurement. So I'm hoping that I didn't go too far over, and maybe I'll be happy to take more questions as I can.
No, you didn't. That was perfect and a fascinating talk. So first of all, I just really want to thank you. I'm sorry we can't all applaud in person as we normally would, but we're applauding from home. I'm applauding now. Maybe you hear me. And I could easily ask you questions for another hour, but instead let other people and open it up, especially to those of you who might not have been interrupting during the talk. Go ahead.
Could I, Ephraim, can I just pop in here? Could I just a clarification, Jonathan? When you talked about preparing something in a state and then doing a weak measurement and then following it by a strong measurement and so on, is that you have one system and you do one thing to it and then you do another thing to it? Or are you imagining a large number of copies of that and doing conditional things and so on and so on?
Yeah, this is with the same system for the first, part of its life. For the first 100 nanoseconds, we weakly measure, and then right after that, same system, immediately after the measurement, we strongly measure.
I see. Okay, so it's okay. That's good. Thanks. Thanks.
Mm-hmm.
Other questions? You can either jump in or raise your hand, and I'll try to see if that shows up on my screen. I do think that there was another question. Someone had already started typing into the chat before. Was that Noah again, or did it already get answered? All right. Well, honestly, since we are a little bit over and have a tight schedule of other meetings, I think we'll hold on to you, Jonathan, and meet with you with my group. But instead of having more public questions, let's just thank you one more time. It was really a great talk and very provocative. I'm sure we'll all be debating some of it for a while.
Yeah, I'm looking forward to the discussions.
Thank you.
Great. All right. Bye, everyone, except our gang. So between us, I know you must have already said it a few times. Maybe it's the same thing that John was getting at. But when you talk about the weak measurement reducing the entropy of the subsequent strong measurement, I don't actually expect that to happen. Are we really talking about a conditional entropy as opposed to a total entropy?
Yes. So when I say that the entropy decreases, I guess it's kind of an apples to oranges comparison, because